The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So welcome back, everybody. So this is the final exam checklist. For the single oscillator, we need to make sure that you know how to write down the equation of motion. We have discussed about damped, underdamped, critical damped, and overdamped oscillators. And we have tried to drive oscillators, and we observe transient behavior and steady state solution. Resonance, right? So which we actually demonstrated that by breaking the glass. And then we move on and try to couple multiple objects together, and that brings us to the coupled system. What are the normal modes, and how to actually solve n-1k matrix eigenvalue problem, right? And what is actually the full solution for the description of coupled system? And can we actually drive the coupled system? And we found out we can, and also the system will respond as well, similar to what we have see in the single oscillator case. We see resonance as well. We can excite one of the normal mode by driving the coupled system. And then we put more and more objects, and until at some point we have infinite number of coupled objects. What is actually the solution of refraction and the transmission, refraction and the translation symmetric system, right? So that is actually a discussion of symmetry. We go to the continued limit. We actually found wave and wave equations, right? So we found that finally we make the phase transition from single object vibration to waves, and that is actually an achievement we have done in L3. And we have discussed about different systems: massive string, massive spring, sound wave, electromagnetic waves, and we have discussed the progressive wave and the standing waves. For the bound system, we have also normal modes, and we discussed about how to actually do Fourier decomposition and what is actually the physical meaning of Fourier decomposition in L3. And for the infinite system, we also learned about Fourier transform and uncertainty principles. And we actually learned to apply boundary conditions so that actually we constrain the possible wavelengths of the normal modes. And therefore, we also learned about how to actually put a system all together. And finally, how to actually determine the dispersion relation, which is omega as a function of k, the wave number. So until now, we actually discussed idealized system, and we also move on to discuss dispersive median. So we have learned even more about dispersion relation for the dispersive median, and signal transmission, how to actually send signal, right, through a highly dispersive median, right? The solution we were proposing is to use a amplitude modulation radio, and that solves the problem of dispersion. And the group velocity and phase velocity, we covered that, and also, as I mentioned before, the uncertainty principle. A 2-3D system, so we have bound system, which we have normal modes for 2-dimensional and 3-dimensional system as well. You can see normal mode all over the place. So just make sure that you know how to actually derive all those standing waves for different dimension of system. And we actually showed and proved geometrical optics, which is actually a direct consequence of waves wave function, continuation of the wave function and boundary condition. And we learned about the refraction rule and also Snell's law. We talk about polarized waves, linearly, circularly polarized, elliptically polarized, and the polarizer and quarter wave plate. And at the end of the discussion of 2,3D system, we actually discuss about how to actually generate electromagnetic wave by accelerated charge. Okay. Finally, we went on and talk about how those EM waves propagate in dielectrics, and again, boundary condition, which leads to interesting phenomena, which belongs only to electromagnetic waves. For example, Brewster's angle, right? And also the refraction amplitude. Refractive wave amplitude is actually governed by the property of the electromagnetic waves, which is actually the coming from the laws which governs electromagnetic wave, which is Maxwell's equations in matter. And we were trying to also manipulate those waves by adding them together. And we see constructive and destructive interference and diffraction phenomena. And then we connect that to quantum mechanics by showing you a single electron interference experiment. And that connects us to the beginning of the quantum mechanics, which is actually probability waves, which is actually different from all the waves we have been discussing. But you are going to learn a lot more in AO4. Okay, so don't worry. All right, so that is actually the checklist. You can see that I can write it in 2 pages, so it's not that bad, probably. And I hope that there was nothing really sounds like new to you by now, right? If you find anything is new, you have to review that part. That means you missed the class. All right, so what I'm going to do now is to go through all the material faster than the speed of light, all right? So that you will get nothing. No, you are going to get a list of the topic. And you just have to feel it. If you feel good, like when you are having a cupcake, right? Then you are good for the final. If you don't feel good, like, what is Professor Lee talking about? He's talking about nonsense now. Then you are in trouble, and you have to review that part, all right? Okay, so that's the rule. So let's start. All right, so why AO3? So we started the discussion. Oh, welcome. We started the discussion of AO3, and it's vibration and waves, so it's the name of this AO3. And the motivation is really simple because we cannot even recognize the universe without using waves and vibration, right? Then you cannot see me, and you cannot hear anything, and you cannot feel the vibration, the rotation of a black hole by your body anymore. Then it's not very cool, right? So therefore, we actually study AO3 to understand the basic ideas about waves and vibrations. And we found that wave and vibrations are actually interesting phenomena. Waves are actually connected to vibration because if you look at only, for example, a single object on these waves, you actually see that it's actually a single object which is oscillating up and down, and this is actually vibration. So there's a close connection between single particle vibration and the waves. And that is actually the first thing we actually learn. Therefore, we need to first understand the evolution of a single particle system. And we make use of this opportunity to actually start the discussion of scientific method, right? So using this opportunity, basically what we have been doing for the whole class is the following. So the first step is always to translate a physical situation which we are interested into mathematics, right? Because mathematics is the only language which we know which describes the nature. If you come out with a new language, and that is going to be a super duper breakthrough, it cannot be estimated by Nobel Prize. But the problem we are facing now is that this is the only language we know which works. Therefore, we actually really follow this recipe for which is actually similar to many other physics class. And we have a physical situation. We use laws of nature or models, and we have a mathematical description, which is the equation of motion. And this is actually the hardest part because you need to first define a coordinate system so that we can express everything in a system. In that system, then you can actually make use of the physical law you have learned from the previous L1 and L2 to write down the equation of motion. And most of the mistake and also most of the problem or difficulty you are facing is always in this step, actually. Then we can actually solve the equation of motion, which is actually strictly speaking not my problem. It's a math department problem, okay? And yeah, that's their problem, anyway. Then we solve the equation of motion, and you will be given the formula. Then we use initial conditions and make prediction. And we would like to compare that to experimental result. And that is actually a general thing which we have been doing for physics. So let's actually take a look at those examples. Those are examples of simple harmonics motions. And you can see that this all the systems have one object which is actually oscillating. And you can see that actually their equation of motion are really similar to each other. It's theta double dot plus omega 0 squared, theta equal to 0 for those idealized simple harmonic motion. And we actually learned that the solution of those equations actually the same, which is a cosine function. Then we actually went ahead and add more craziness to the system. So basically what we actually tried to do is to add a drag force, right, into the game. And we were wondering if this more realistic description can actually match with experimental data. Right? So this is actually the equation of motion, and the additional term is actually the one in the middle, the gamma theta dot term. And after adding this term, not only it is actually an interesting model to describe the physical system we are talking about, but the mathematical solution is far much more richer than what we actually talk about in the single harmonic oscillator case. Basically, you will see that the general solution depends on the size of the gamma compared to omega 0, which is the oscillation, the natural frequency of the system. Okay, and you can see there are three distinct different kinds of solution. They have different mathematical form, and we call them underdamped solution, critically damped solution, and overdamped solution. Okay, so those equations will be given to you, and the excitement is the following. So you can see that those solutions, if you plot the solution as a function of time, they look completely different as a function of time, right? So in the case of no damping, the amplitude is actually constant. It's not actually reducing as a function of time. And but when the damped system actually, the damping is turned on, then in the underdamped situation, you can see that the amplitude is reducing as a function of time. And if you have too much damping, you put the whole oscillator into some liquid, for example, and you see that the oscillation actually disappears, right? The cool thing is the following. The excitement from as a physicist is that all those crazy mathematical solutions actually match with experimental result. Wow, that is actually really cool, right? Because there is nobody say that this should match, and how nature actually learn that, okay, when should I actually change the behavior of the system, right? So this is actually really a miracle that this complicated mathematical description actually is useful. and it is actually super useful to describe the nature, okay? So once we actually have learned that, we can now add a driving force into the gain, okay? So from the equation here, we can see that there's a natural frequency omega 0 of this system, and there's a drag force term, which is actually to quantify how much drag we have a gamma there, okay? And we are driving it at a driving frequency omega d. So what we have learned from here is that if you are driving this system, for example, I'm shaking that student, shaking you, okay? In the beginning, this student is going to resist, no, don't shake me, come on, right? But at some point, he knows that Professor D is really determined. Therefore, he is going to be shaken at the frequency I like, okay? So that is actually what is happening here. So this is so-called the transient behavior, right? So in the beginning, the system doesn't like it, right? So this is actually making use of the superposition principle, right? So you can solve the homogeneous solution, which is actually in the right-hand side. It depends on the physical situation you are talking about. You choose the corresponding homogeneous solution. And left-hand side is actually the driving force from Yen-Jie, right? And that is actually going to win at the end of the experiment, right? Because I'm going to shake it forever until the end of the universe, right? So you can see that at the end, what is actually left over is really the steady state solution. And it has this structure A omega d, depends on omega. And you get resonance behavior. Don't forget to review that. And also you have delay in phase, because when I shake the student needs some time to respond, right? Therefore, the delta is actually non-zero if the student is damped, okay? All right, so now we have learned all the secrets about the single object system. Then we can now go ahead and study coupled oscillators. There are a few examples here, which is coupled pendulums or coupled stream mass systems. And we found that a very useful description of this kind of system is to make use of the matrix language, okay? So originally, if you have n objects in the system, you have n equations or motions, and that looks horrible, right? But what is actually done in L3 is that we actually introduce a notation with a matrix. Basically, if you write everything in terms of matrix, then it looks really friendly, right? And it looks really like a single oscillator, right? Okay. Although solving this equation is still a little bit more work, okay? And basically, we can see that from this example, we can actually derive n-1k matrix. And the whole equation of motion problem-solving problem become n-1k matrix eigenvalue problem. What is actually n-1k matrix? Okay, this is actually describing how each component in the system actually interact with each other, right? So once we have this, we can actually solve the eigenvalue problem, and we are going to be able to figure out the normal modes of those systems. So what is actually normal mode? Normal modes is a situation where all the components in the system are oscillating at the same frequency and also at the same phase. Okay, so that is actually the definition of normal mode, and also actually what is actually used in the derivation also, which leads us to the eigenvalue problem. We define z equal to exponential I omega t plus phi. Everybody is actually oscillating at omega and also a phase phi, right? So that is actually what we actually learned. And what is actually the physical meaning of those normal modes? So if we plot the locus of the two coupled pendulum problem, what we actually see is the following. So basically, you will see that the locus looks like really complicated as a function of time if you plot x1, x2 versus time. But if we rotate this system a bit, then we find that there's a really interesting projection, which is the principal coordinate. You see that actually all those crazy, strange phenomena we see with coupled system are just illusions. Actually, you can understand them by really using the right projection, okay, to the right coordinate system. Then you will see that actually the system is doing still simple harmonic motion. Okay, so that is actually the cool thing which we learned from a coupled system. So we learned about how to actually solve the coupled system, and we also learned about going to infinite number of coupled system. Okay, so then this is an example here. So for example, I can have pendulum and springs, and we connect them all together, and I need to hire many students so that they praise it, or the praise until fill up the whole universe, right? So this is actually the idea of infinite system, okay? And you can see that means my n minus 1k matrix is going to be an infinite times infinite long matrix. Okay, it's two-dimensional, and the A is infinitely long, and that sounds really scary. And in general, we don't know how to deal with this, really, okay? And it can be as arbitrarily crazy as you can imagine, okay? So what we actually discuss in AO3 is a spatial case. Basically, we are discussing about systems which are having a spatial kind of symmetry, which is translation symmetry, as you can see from all those figures. And you can see that all those figures will have to all have the same normal modes, right? Because of the space translation symmetry. What we actually discussed about is that we introduce a S matrix, which is actually used to describe the kind of symmetry that this system actually satisfies, right? And if we calculate the commutator S and the n minus k matrix, if this commutator shows that if you evaluate this commutator and you get 0, that means they commute, and the consequence is that the S matrix and the n minus 1k matrix will share the same eigenvectors. Okay, so you don't really need to know how to derive this conclusion to arrive this conclusion, but it is actually a very useful conclusion. So that means instead of solving n minus 1k matrix eigenvalue problem, I can now go ahead to solve the S matrix eigenvalue problem, and usually that's much easier. Okay, so for the exam, you need to know how to write down S matrix. You need to know how to solve eigenvalue problems, including n minus 1k matrix and the S matrix. And then we can actually get the normal mode frequency, omega squared, and we can also solve the corresponding normal modes. And here is actually telling you what will be the solution for a space translation symmetric system. And basically what you see is that making use of the S matrix actually brings you to the conclusion that Aj must be proportional to exponential ijk, where this A is actually the length scale of this system, the distance between all those little mass. And the J is actually a label which tells you which little mass I am talking about. And K is actually some arbitrary constant. But by now, you should have the idea, basically, that's what? that is actually the wave number, right? So that is really cool. So that's all actually planned in advance. And basically, you can see that we can also write down the AK because we know that AJ will be proportional to exponential IJ KA after solving the eigenvalue problem for S matrix. Then we actually went one step forward to make it continuous, right? So basically, we make the space between particles very, very small. And also at the same time, we make sure that the string doesn't become supermassive, right? And we actually concluded that we get some kind of equation popping out from this exercise. N minus 1 K matrix becomes minus T over rho L, partial square, partial K, X squared. You don't have to really derive this for the exam, but you need to know the conclusion. And then phi psi j becomes psi as a function x and t. And the magical function actually appeared, which is the wave equation. Oh my God, this is the whole craziness we have been dealing with the whole AO3, right? Then this is actually really remarkable that we actually can come from single object oscillation, putting it all together, make it continuous. Then this equation really pop out, and this equation actually really describe multiple systems. Then we went ahead to actually discuss the property of the wave equation. It looks like this. Basically, I replaced the T over rho L by Vp squared. By now, you know the meaning of Vp is actually the phase velocity. And we discussed two kinds of solutions, spatial kind of solution. The first kind is normal modes. The second one is progressive wave solution or traveling wave solution, whatever name you want to call it. Let's actually take a look at the normal modes, what we have we learned. So if you have a bound system, in bound continuous system, the normal modes are actually standing waves for the wave equation we discussed. And basically, the functional form is an sine knx plus alpha m and sine omega t mt plus beta m. Okay, so what we actually learned from the previous lecture is the following. So basically, you can actually decide the Kn and alpha n by just boundary conditions, right? So before you introduce boundary conditions, which are the conditions allow you to describe multiple nearby systems consistently. Okay, so that is actually the meaning of boundary condition. Before you introduce that, Kn and alpha n are arbitrary number. Whatever number you can you choose is actually can satisfy the wave equation. But after you actually introduce the boundary condition, you figure that out from the problem you are given. Then Kn and alpha n cannot be arbitrary anymore, and they usually become discrete numbers. Okay, so that is actually what we actually learned from the previous lectures. And finally, we will also see that omega n is actually determined by the property of the system by so-called dispersion relation. In this case, it's linear, it's proportional to Km, because we are talking about non-dispersive median for the moment. And we have this beta m, which is actually related to the initial condition, and the Am, which can actually be determined by Fourier decomposition, right? So if you are not familiar with this, you have to really review how to do Fourier decomposition, okay? I know most of you actually did very well in the midterm, but maybe some of you actually forgot how to actually determine Am, and it will be very, very important to review that for the preparation for the final. Now the second set of solution is the following. So you have progressing waves, and the functional form is really interesting. So you can see it's actually can be written as f f is actually some arbitrary function, x plus minus vpt, right? Basically, that is actually describing a wave which is traveling to the positive, to a negative or positive direction in the x direction. And or you can actually write it down as g function kx plus minus omega t. Actually, they all works for wave equations. Now we actually went ahead and applied the approach which we learned from the general solution of wave equation to massive strings, and we discussed about sound waves, right? For the sound waves, it will be important to actually review what are the boundary conditions for the displacement of the molecule in the sound wave. Compare that to the pressure deviation from the room pressure, okay? So I think it's important to make sure that you understand the difference between these two, what are the boundary conditions, and basically it should actually be very similar to the solution, the boundary condition for the massive strings. And we also talk about electromagnetic waves, right? And that is actually another topic which you really have to review. And several things which is actually interesting is that electric field cannot live without magnetic field, right? They are always together, no matter what, right? So if you have a traveling electric field, then there must be a traveling magnetic field. And that is actually governed by the Maxwell's equation. Because before we actually go into the detail of those, we also discuss about dispersive median, right? So in the case of dispersive median, we actually use a special kind of example, which is strings with stiffness, right? So basically, what we actually found is that if you have a certain kinds of wave equation, like this one, yeah, I'm actually writing this one here. Basically, if I add the additional term to describe the stiffness, right? Then what is actually going to happen is that the dispersion relation, when I ask you to plot the dispersion relation, usually I am requesting you to find the relation between omega and the k. And I'm going over this in more detail because I see so many similar mistakes in the midterm. So basically, what I'm asking is omega versus k. And if we don't have this term, then basically you have a straight line. Straight line means you have a non-dispersive median, right? And if you add this term, you need to know how to evaluate the dispersion relation. The quickest way to evaluate the dispersion relation is to just simply plug in the progressing wave solution, for example, the G function or harmonic progressing wave solution sine omega kx plus minus omega t into this equation, then you will be able to figure out the dispersion relation. And what we actually figure out is the following. If we actually include stiffness, then you can see that the dispersion relation is not a line anymore, and it's actually some kind of curve, and the slope is actually changing. Okay, and there are geometrical consequences from this thing, right? That means if I have a traveling wave, okay, with different wavelengths, that means the phase velocity Vp equal to omega over k is going to be different for different waves with different frequency or different wavelengths. Okay, so that is actually clearly a problem, because if I have initially produced a signal which is a triangle and I let it propagate, what is going to happen is that the slow component will be lagged behind. Those are the slow component. And the fast component will go ahead of the nominal speed, right? So there will be a spread of the signal. Originally, maybe you have some kind of square wave, and this thing will become something which is actually smeared out in the space, and you lose the information. And we are going to talk about that later. And we also learned about group velocity. So what is actually group velocity? Group velocity Vg is actually partial omega partial k, right? Which is actually the slope of a tangential line here, and while the phase velocity is actually connecting this point to that point, and the slope of this line is actually the phase velocity, and the slope of the line cutting through this point, which is actually giving you the group velocity. And we actually learn the definition of the consequence of group velocity and phase velocity by introducing you a bit phenomena. Basically, we add two waves with similar wavelengths or wave number. Basically, what we see is the following. So basically, you see some behavior like this. You see the superposition of these two waves, which produce a bit phenomena, can be understood by something which is actually oscillating really fast, modulated by a much slower, more varying envelope. Basically, you can actually understand the bit phenomena by decomposing, by actually identifying these two interesting structure. And the speed of all those little peaks is actually traveling at the phase velocity, and the speed of the envelope is actually found to be traveling at group velocity. Okay, so that is actually what we have learned, and we can have group velocity and the phase velocity traveling at in the same direction. And we can also have negative group velocity, right? So that is actually a technique which is really, really very difficult. And I'm still trying to practice and make sure that I can demo that in AO3. Basically, it's like the whole system, the whole little structure are actually moving in a positive direction. But the body, or say the envelope, is actually moving in the negative x direction. So that is actually also possible, and you can actually construct a system which have negative group velocity. So once we have done that, we actually also try to understand further the description of the solution for the dispersive median. Right? So basically what we actually went over during the class is that, okay, now if the f function f of t is describing Yen-Jie's hand, and I'm holding infinitely long string, and I shake it as a function of time, and that is actually, this motion is actually described by this f function, okay? What we actually know is that this oscillation, okay, I can do whatever I want, but all kind of f function can be described as superposition of many waves with different angular frequency. Okay, so that's a miracle which we borrow from the math department again, and you can see that f function can be written as a sum of all kinds of different waves with different angular frequency with population c omega. This is actually the weight which actually make them become the f function. Okay, and we can actually figure out the c omega by doing a Fourier transform, and finally, what will be the resulting wave function psi xt, which is actually the wave function generated by the oscillation of my hand, and also governed by the wave equation, which give you the relation between omega and the k, can be written in that functional form. Okay, so the good news is that with the help of Fourier transform, we can actually also describe and predict what is going to happen, no matter if this system is dispersive or not dispersive, using this approach. Okay, so that is actually really cool. And you can, of course, can do a cross-check just to assume that this is a non-dispersive median, and you are also going to get back to what you should expect the solution to non-dispersive median for the psi xt. So that is actually one thing which is really remarkable, and I think what is actually needed to know is not the deviation of all those formula, but how to actually plug in and derive C omega, right, by using the formula you are given, and how to actually then put together all the solution and become the resulting solution for the psi xt, which is actually really the solution we really care. Okay, so for that you need to know how to do the integration. You need to know how to derive the dispersion relation. Then what is actually left over is to plug them into that equation, which is actually also given to you in the formula. And we will not ask you to do very, very complicated integration for sure in the final. So what is actually the consequence? So basically, one thing which is interesting to know is that if you have waves in the coordinate space, which is actually really widely spread out, and you can do a Fourier transform to get the wave population in the frequency space, what we found is that when this wave is really, really wide in the space, then what we found is that actually the wave population in the frequency space is very narrow, okay, by using Fourier transform. That is actually the result. And on the other hand, if you have a very narrow pulse in the coordinate space, for example, I do this really quickly. All right, I create a very narrow pulse, and what is actually happening is that I will have to use a very wide range of frequency space to describe this very narrow pulse. Okay, so that leads to direct consequences of that is uncertainty principle, and this is actually closely connected to the uncertainty principle we talk about in the quantum mechanics. Delta P times delta X greater or equal to h bar over 2. All right, so we have done with the one-dimensional case, and we also talk about two-dimensional and the three-dimensional case. And this is actually an example of two-dimensional membranes, and they actually are constrained so that their boundary condition at the boundary is equal, the wave function is equal to 0, and you can actually identify all those normal modes. And we went ahead also to talk about geometrical optics laws. Basically, how do we actually derive that is to have a plane wave. First, you have a plane wave propagating toward the boundary of two different median. And we were wondering, well, what is actually the refractive wave and the transmitted wave? By using the, by making sure just one point, which is that the membranes doesn't break. Okay, the wave function is continuous at this boundary. That's the only assumption which we use. We went through the mathematics, which you don't really need to remember all of them, but you really need to remember the consequence. The consequence is the following. So basically, what we see is that if you have incident plane wave with incident angle theta 1, the refractive wave will be having an angle of theta 1 as well. So that's actually the first law of refraction law. And the second one, which we learned, is that the transmitted wave will satisfy Snell's law, n1 sine theta 1 equal to n2 sine theta 2. And that is actually very interesting because this Snell's law, okay, have also nothing to do with Maxwell's equation. You see, right? That's actually what you actually can learn from here. We usually use electromagnetic waves to demonstrate Snell's law, right? But from LO3, you learn that it has nothing to do with Maxwell's equation. It applies to all kinds of different systems which can be described by wave functions. So that is actually the very important consequence. But on the other hand, as we will discuss later, the relative amplitude of the incident wave, refractive wave, and transmitted wave, the relative amplitude is governed by Maxwell's equation. So I would like to make that really critically clear. So the relative amplitude is governed by really the physical laws, which actually governs the propagation of those plane waves. Okay, so I think we can actually take a 5-minute break to have some air. And of course, we are welcome to continue to use all those juice and the coffee. And coming back at 38. Okay, so welcome back, everybody, from the break. So we are going to continue the discussion. So we have actually learned about the two important laws for the geometrical optics. And we actually also went ahead to discuss the polarization itself in greater detail. So for example, we can have linearly polarized wave. So basically, the waves is actually moving up and down, but the direction of the vector field doesn't change. Okay, it's always, for example, initially if it's in the x direction, then it's actually at the x direction forever. And in that case, I call it linearly polarized. Okay. Of course, I can also have the case that I can actually have a superposition of two waves. One is actually having the electric field in the x direction, and the other one is actually in the y direction. And they are off by a phase of pi over 2. If that happens, then basically you will see that it produces something really interesting. The direction of the electric field is going to be rotating as a function of time, as a function of the space this wave actually travel. And that we actually call it circularly polarized waves. And we can also have elliptically polarized wave. Then we learned about how to actually do a filtering, which is actually the polarizer. So suppose I have a perfect conductor here, where I have the easy axis, which is actually described by the green arrow there. And you can see that easy axis means that if you have electric field parallel to the easy axis, okay? And then since that's an easy axis, so it's supposed to be easy, therefore this electric field is going to be passing through the polarizer. On the other hand, if the electric field is perpendicular to the direction of the easy axis, that means it's taking the perfect conductor in the hard way. Therefore, when it when it is trying to pass through the perfect conductor, the electrons in those conductors is going to be working like crazy to refract this wave when the direction of the electric field is perpendicular to the direction of the EZ axis. Okay, so that is actually how things actually works. For example, so in the first example, you can see that in this case, you have EZ axis, which is actually perpendicular to the direction of the electric field, which is the red field. Then this wave is actually got refracted. There will be no transmission. No electromagnetic field passing the perfect conductor. And on the other hand, if you have another perfect conductor, which you have EZ axis, which is actually parallel to the electric field, then you can actually you will see that actually it will pass through the perfect conductor. Okay, so that is actually the polarizer, and also we discussed about quarter wave plate, which I would suggest you to have a review about the concept which we have learned about polarizer and quarter wave plate, so that you make sure that you understand how to actually calculate the electric field after passing through polarizer and the quarter wave plate, and how the circularly or elliptically polarized wave are created using all those wave plates, etc. Okay. All right. So the next thing which we actually discussed during the class is how do we actually produce electromagnetic waves. I think by now you should actually know that a stationary charge doesn't produce electromagnetic wave. Even a moving charge at constant speed doesn't create electromagnetic wave. So how do we actually create electromagnetic wave which propagate to the edge of the universe? That is actually, the trick is to create a kink in the field line, right? So you have to accelerate and stop it, okay? Accelerate and try to actually stop the acceleration, okay? So then you can create a kink, okay? And this kink is going to be propagating out of the as a function of time, and this kink is actually creating the so-called radiation from this accelerated charge. So you don't really need to remember all the derivation, but you really need to know the conclusion. So what is the conclusion? Is about the radiated electric field is actually equal to minus, very important, there's a minus sign in front of it, which is a common mistake to drop it. And the Q is actually the charge of the accelerated charge, right? Proportional to the charge, right? If the particle is more charged, then you have more radiation. A perp is actually the acceleration projected to, which is the perpendicular projection of the acceleration of the particle with respect to the direction of propagation is actually so-called A perp, and only the perpendicular direction acceleration actually counts. Okay, the one which is actually parallel to the direction of the propagation doesn't really count, as you can see from this equation. And the T prime, what is T prime? T prime is actually T minus R divided by C. So T prime is the retarded time. So that is actually telling you that it takes some time for the information to propagate from the origin, which is the position of the moving charge, to the observer, which is actually R, this distance away from the moving charge. Okay, so the information takes some time to propagate, and you cannot know what is actually really happening. For example, 100 light years away from Earth, right? You have no idea about what is happening. Maybe a black hole is created there, and it's going to suck us everybody up in a few years, but nobody knows, and we don't care because we cannot control. All right. All right. So that is actually very important, and also very important to know the magnetic field must be there, you can see the relation between magnetic field and the electric field, and the pointing vector is actually also shown here. And when we actually went ahead, given all the knowledge we have learned, we discussed about how to take very beautiful photo using polarizer filter, and we discussed about how to filter out the scattered light from the sun, and it would be nice to figure out why this is the case, how this polarized light, the scattered lights are created. Okay, it's purely geometrical. And also we discussed about Brewster's angle, and also how actually that actually lead to the explanation of the filtering of the light, the refracted light from the, for example, window of a car or from the water. And this is actually a demonstration of the summary of Brewster's angle. So actually, so somebody reminded me that the amplitude should be given. So I think if this is actually the amplitude formula for Brewster's angle will be given to you if that is actually asked in the final exam. So don't be worried about it, and you don't have to remember this formula. And I'm not going to ask you to derive that just in such a short time, like 3 hours in the final exam. But what is actually very important is to know how this Brewster's angle, why there's no refracted light polarized in a way that the polarization should be why the refracted light is actually polarized, for example, and also why the transmitted wave is actually slightly polarized. And I think the conclusions you need to remember, and you need to know how to calculate the angle at least, right? Because for this purely polarized light to be produced in the refracted light, you need to have normal angle between the direction of the refracted light and the direction of the transmitted light. And that you should be able to remember, right? And you should be able to derive that also from your mind as well, because that means the direction of the oscillation of the molecule at the boundary will be actually in the direction of propagation of the refractive ray. Therefore, that cannot be a solution to the progressing electromagnetic wave. Therefore, the refractive waves are polarized, right? So if you follow this logic, then you don't really need to memorize all those formulas. All right. So finally, in the last part of the course, we focus on the superposition of many electromagnetic waves. So it can produce constructive interference, or that means all those waves are in phase, right? And you can have destructive interference when they are out of phase, okay? And that is actually a very important topic. You should review that for the preparation of the final. And you can see that there are 3 concrete examples which we use during the class. A laser beam, we talk about water ripple in the demo, and we also studied how to actually make use of this phenomena to design a phased radar. So to detect this unknown object on the sky, what we actually really need to have electromagnetic wave pointing to a specific direction, and that can be achieved by using multi-slit interference. And this is actually the property of the 2-slit interference pattern, and you are going to have many peaks. They have equal height, right, for 2-slit interference if you ignore any effect coming from diffraction, okay? So if we assume that the slit is actually infinitely small, right? The slit is super narrow, and then we can actually ignore the diffraction single slit diffraction effect, then all the peaks due to this two slit interference will have the same height. On the other hand, when we actually start to increase the number of slits, for example, n equal to 3, n equal to 4, n equal to 5, n equal to 6, as you can see that the structure of the intensity as a function of delta, which is the phase difference, is actually changing. And you can see that the general structure is the following. So if you have n equal to 3, then basically you have 2 adults, and between them you have 1 child. And if you have n equal to 6, then basically you have 2 adults, and somehow there are 4 children in this collection, right? So basically that is actually what we actually learn from the solution of the multi-slit interference. And in this way, we can actually make the width of the principal maxima as narrow as you want, okay? So that is actually why phased radar actually works. And then we discuss about diffraction. So that is actually related again to the explanation of laser beam. And we discuss about the design of a Star Trek ship, the gun for the ship. And we also talk about resolution. And what is actually happening here is the following. A single slit diffraction is actually can be viewed as infinite number of source interference, right? And you just need to integrate over all the point-like source between the two walls, and all of them are acting like a spherical wave source, right? So basically, for every point, continuously, every point between these two walls are a point source of spherical wave. And that is actually Huygens principle. And we can see that the structure is, of the intensity as a function of position is the following. So basically, you have a principal maxima, which is actually a peak at in the middle. And at some angle, basically, you have destructive interference such that if you integrate over all the contribution from infinite number of sources in this window, basically, you will see that they completely cancel each other. So that is actually the origin of all those, the deep structural minima. And then after the minima, actually, you will see another peak, but the height of the peak is actually suppressed by 1 over beta square. And it would be good to review that. And what is actually the consequence? So if you shoot a laser beam to the moon, basically the size of the laser beam will be very large. After you learn AO3, you know that the size of the laser beam is going to be very, very large due to interference between all the point-like source from your laser plane. Okay, and finally we actually can put them all together. So the single slit diffraction and the multi-slit interference, you can put them all together, and basically what you get is the following. So basically you have a multi-slit interference pattern, which is shown there, but now the intensity of the multi-slit pattern is modulated by the single slit diffraction pattern, and of course the full formula will be given to you. But on the other hand, you are also requested to know how to actually calculate, just to add the contribution from multi-slit together in case if we actually change the amplitude of the incident light, or we change the phase, like what we actually did in the homework. Okay, and I think that is actually one important point, and you should actually review that. And if you are not sure about how to proceed with that, it would be good to review lecture 20 to lecture 23. So finally, we talk about the connection to quantum mechanics. So Einstein already told us that I have set so many times, God doesn't play dice with the world. But what we actually found is that there are two very interesting things which we found. The first thing is that if we have a single photon source, and basically if we don't play dice, we cannot actually explain the intensity of the after this single photon source pass through two polarizers. And what happens is the following. So basically the result of a single photon source tells you that you really need to play dice so that you can actually get the resulting polarized light intensity. And also the second pseudo experiment we actually discussed is that if you have video board, basically you have and have them pass through the two-slit experiment, basically you are going to get is two piles Gaussian-like distribution. And if you have a single electron source, what it does is that it actually interfere with itself. An single electron can interfere with itself and produce a pattern which is actually very similar to what we see in the double slit interference pattern. So that is actually really remarkable. And also we talk about a single slit, single electron experiment. Basically that give you also diffraction pattern. We have to use the wave function to describe the position, the probability density of the position of the electron on the screen, and that is actually closely connected to the uncertainty principle, which we actually discussed earlier. Delta p, delta x greater than or equal to h bar over 2. So if you have a very narrow window, that means you have very small delta x. So you have very, very good confidence about the location of the electron. And then the momentum is in the x project. The momentum in the x direction, you have large uncertainty according to this equation. And that is actually can be seen from this single slit diffraction pattern, and is closely connected to what we have learned before. So where's this, how to actually describe the, what is actually really the dispersion relation, okay, of the probability density wave is actually coming from Schrödinger's equation, and this is actually given here. We actually briefly talk about that. And the consequence is the following. So basically, you can actually describe the evolution of the wave function as a function of time by using this wave equation. And this wave equation is actually slightly different from what we actually have learned before. And we also can use what we have learned from AO3 to solve a particle in a box problem, which is actually covered in lecture number 23. And I just want to say that you need to know the general principle, but I'm not teaching AO4, so I'm not expecting you to solve quantum mechanics problem. But I would like to say that, okay, from this point, it's actually motivating you to take AO4, right? Because there can be a lot of fun there as well, and it's actually closely related to what we have learned from AO3. So I just want to say, in the last point is that this is actually really not the end of the vibrational waves. It's just the beginning, and there's a path toward the peak, and it may take a long time to reach the peak. All right, and I would like to let you know that I'm really, really very happy to be your lecturer this semester, and I really enjoy teaching this class and getting your response when I ask questions. Thank you for the support, and I would like to say good luck with the final exam, and we have 800 contribution on Piazza. Many thanks to Yen, who is actually doing all the hard work day and night. And thank you very much, and see you around in NIT in the future. Thank you.